Welcome to Quantum Photonics. So, we are here with a very interesting topic, and we have a very special guest speaker. And at the outset, I'd like to say that Peter, in case there are questions that, because English is not his first language, and sometimes since we're talking technical, there might be some questions that he would not. Peter would not be able to process immediately. So probably some people can write it down, or we can take it for maybe the next session. Just mark the questions. So, however, just let us know, Peter, if you need that for some questions that might come up later. So, yeah, to introduce the topic, um, we grapple daily with the complexities of describing reality on both cosmic and microscopic scales. Theories such as general relativity and quantum mechanics have provided invaluable frameworks, yet they stand apart, seemingly irreconcilable in their approaches. In a recent publication in Frontiers in Physics, our guest speaker had put forth a method that challenges this dichotomy, and to this, he tries to enter the Alena Tensor, an elegant mathematical construct that offers a tantalizing prospect, which is the ability to manipulate the curvature of space-time, akin to adjusting a slider. This means transcending the traditional boundaries between curved flat space-time and seamlessly transitioning between descriptions grounded in general relativity and those rooted in quantum mechanics. And the implications are profound. Not only does this method promise to shed light on long-standing enigmas such as dark matter and dark energy, but it also hints at a unified framework for understanding the fundamental forces of nature. Gravity, electromagnetism, and potentially other fields can be harmonized within this novel paradigm. However, amidst the allure of this newfound synthesis lies a profound existential question. What is the true nature of the universe? Could it be that our reality is but a fluctuating field, and space-time merely a perceptual lens through which we observed it? While this proposition opens doors to unprecedented insights, it also demands rigorous scrutiny and further exploration. The journey ahead is rife with challenges, but the promise of unraveling the mysteries of our cosmos beckons us forward. Let's listen to our guest today and check out possibilities of unveiling the secrets of the universe and reshape the landscape of modern physics. So, to tell you more about our guest speaker, Dr. Peter Ogonowski is an experienced researcher, manager, and lecturer. A manager of over 20 years of experience, lecturer, author of a series of lectures and trainings, researcher, author of publications in physics and management. In 2010, he was selected as one of the 4 experts consulting planned changes in the rule for co-financing innovative projects from the EU funds in Poland. In the years 2018 to 2022, he was a member of the expert group in auxiliary body at the Chancellery of the Prime Minister of Poland. He conducts classes for 1 and 2 degree studies and for MBA students at Kosminski University, University of Management and Banking, University of Logistics, University of Personnel Management, and the National School of Public Administration. So yeah, I'm very proud and very excited to present to you our special guest speaker, Dr. Peter Ogonowski. So Peter, welcome to Quantum Photonics.
Thank you very much. I'm in a very good mood after this music, so I hope it will be really nice speech. So let me tell hi to everyone. Hello. At first, I would like to thank you, the organizers, for the invitation, and of course all of the listeners for the interest in my work. I really think we'll have a very interesting meeting because I'm dealing with very interesting topic. And you will see in a second that it really may change our perception about what the universe is. We'll talk about straightening curved spacetime and about unification of physical theories, because it appears that both these topics are really, really connected. So, since both physicists and science enthusiasts are listening to us, I will try to speak, let's say, understandable language. I mean, understandable for everyone. But at the same time, from time to time, I'll try to use sometimes some more specialized language so that people with physical education listening to us can relate this to their own knowledge. I have also prepared a presentation, and this is available for you. It should be available on the screen, and it will be a really good idea to open it. It's good to see what I'm talking about. Sometimes it's hard to explain something which is quite complicated without pictures, so one picture for 100 words. And for convenience, the slide numbers are large, and I will refer to these numbers when telling which slide I'm talking about. So if you have any questions, just like Cecil said, write them down, because there will be some time at the end and there will be opportunity to ask questions at the end. Okay, we'll start with the agenda from the slide 2. And at first I'll tell you a little about how physics is developing and why this is so difficult to unify it. And we need to start with it to understand exactly what I'm exactly proposing. Then I'll talk about the mathematical object I developed, which is called Alena Tensor. Then I will tell you how to strain curved spacetime and how it can change our perception of the unification of physics. And I will also tell you a few things about how this idea was created and why it's called Alena. And finally, I will say a little about the future. What we can expect next in the connection with this research and so on. So I think we are ready to start. So let's get started. And let me start from some explanation how the science is developing, because most of us think that this is very solid building. So physics, like all science, is not a compact monolith in which successive bricks stand solidly on each other. Physics is made up of people who specialize, and in some sense, they work in their own information bubbles. They read different books, they go to specialist conferences, and over time, their areas of research become a little separated from each other. As you can see on the slide 3, physics today reassembles of group of structures that, of course, are locally solid, but we have trouble connecting them to each other. And moreover, as more solid they are, it's harder to connect it, because you have to prove that you fit into all this construction. And this is not just about the combination of the quantum world and gravity. There are many different inaccuracies that have arisen at the junction of our solidly built but individual buildings. So on slide number 4, you have a fragment of the challenge that physics currently faces. And let's start with the general relativity, which everyone probably has heard about. Okay, so this here it describes gravity in terms of curved spacetime. But when we try to use it in the cosmology, we find that results don't agree with experiment. So at the intersection of general relativity and cosmology, we have added, to be honest, even Albert Einstein added a cosmological constant. And now we have something more. We have a model which is called lambda CMD, which assumes the existence of dark energy and dark matter, so that general relativity can be used to describe cosmological phenomena, and it still works. So we don't know exactly what these dark phenomena are, but that's not the end of the problem. Okay, it's just the beginning. Because when we consider the beginning of the universe and want to, for example, describe the Big Bang, or maybe more precisely inflation, we also have problems. some of these problems results from the fact that general relativity provides non-physical solutions like singularity of black hole, which was, by the way, recently questioned by in his article by Professor Kerr itself. So himself, pardon me. So we need some correction to general relativity to describe very small things. So there is a theory that describes phenomena on a micro scale. Maybe more precisely, this is a set of theories known as quantum field theory. But here we come to problem again. It describes interaction, all of the interaction that don't exist in general relativity, and doesn't describe gravity, which means we have great tool, but this is tool for something completely else, as it looks like now. So everyone is looking for quantum gravity, and I would say this is very popular topic. You will all the time you will hear about somebody has found out something about quantum gravity, because most of energy is exactly on this line of development. But the problem is indeed deeper. After all, we have a non-quantum, classical and relativistic description of electromagnetism within the framework of classical field theory, except that general relativity describes nothing but gravity. So at the same time, we are looking for a way to incorporate relativistic electrodynamics into general relativity. Since we are more or less know how to move from to switch from relativistic electrodynamics to quantum electrodynamics, then we would at least have some starting point on how to create quantum gravity. So at the same time, there are many concepts of, for example, gravitomagnetism and so on. Unfortunately, even if we add that electromagnetism to general relativity, we still would not know how to connect the strong and electroweak interactions with general relativity, because we don't know, we don't have a classical description of electroweak force and strong electroweak interaction and strong interaction. So there is no bridge at the moment between classical field theory and quantum theory, which describes electroweak and quantum chromodynamics. There is only quantum description. Moreover, most physicists indeed believe that there is no such thing like classical description of this interaction, because the world is quantum and cannot be described classically. Hence, the whole discussion between physicists, echo of which you sometimes hear in the media, about whether God plays dice. More precisely, about whether the world is predictable, as in the classical description, or is it quantum, what means unpredictable. So this is not only about curved or flat spacetime. This is also about, can we predict something, or can we just only measure some probabilities? Okay. Somewhere out of the way, there is the whole thermodynamics, which analyzes changes in physics, and this is quite solid theory. But we have also some doubts whether, for example, the lambda CMD model doesn't require giving up, for example, the principle of conservation of energy. And even a quite interesting article on this topic was published recently, by the way. If you look from time to time, you look some how to say it, video blogs on the internet. There's some. This is also mentioned in it. And there's also the last element in this whole puzzle, which is worth attention. And this element, in my opinion, has been neglected. I would say neglected so far. There is a whole branch of physics called continuum mechanics, which describes continuous media, such as water, for example, or dust. Since we don't expect water to flow at speed close to the speed of light, almost all continuum mechanics is based on non-relativistic equations. So we mainly use very classic, old-fashioned equations there. There are, of course, some relativistic additions to continuum mechanics, but they're rather, I would say, selective and rarely used. For example, we don't have a fully relativistic equivalent of the Cauchy momentum equation, which would give us relativistic description of all forces in continuous media, and allow for a smooth transition between classical field theory, for example, and continuum mechanics, which is still, it's not connected. It's not exactly connected. For example, there is a challenge, probably you've heard about this challenge, $1 million challenge, to prove, oh my goodness, I'm stressed about, forgot, Navier-Stokes equations, okay, which is part of continuum mechanics, and it's not proved. So, and this is why I'm speaking about this continuum mechanics, because this is where is the opportunity I saw, okay, and there's opportunity that comes into play, because probably not everyone in the audience know that general theory of relativity describes continuous media, just like continuum mechanics. Moreover, it's known from mathematics. This is nothing special, that any movement under the influence of forces can be represented as a movement along a curved trajectory. So it can be analogously described by the curvatures of the space in which the move itself is straight. I mean, we know how to bend space while leaving the motion path straight to obtain the same effect of calculations. So it's quite easy to make this transformation mathematics for space, but not for space-time. If we could only came up with, I would say, fully relativistic continuum mechanics, it should flow quite naturally into equations equivalent to Einstein's equations. Okay, so Alena Tensor is exactly such solution. You may see it on the slide number 5. Alena Tensor is the energy momentum tensor. What means, maybe for those of us that don't know exactly what is it, it means it's a kind of physical object describing the entire physical system for continuous media. So this is exactly an energy momentum tensor, and at the same time, this is stress energy tensor that is used in continuum mechanics. So it has the following property. This Alena tensor has the following property. In curved space-time, it turns into Einstein field equations, and in flat space-time, it gives exactly relativistic continuum mechanics as well as relativistic Cauchy equation, describing the relativistic forces acting in the system. So this is, of course, it needs confirmation. I mean, this is mathematically seems solid. It was published, it even published twice, because in 2 articles it was already confirmed. But we can say that it works. But when you have such tool, then everything else becomes simple, because from continuum media, one can easily move to classical field theory, and from there to quantum mechanics. Moreover, if we know Lagrange and Hamilton equations, which was, by the way, derived, we can smoothly switch between all these descriptions. So it should be easy. And let me give you an example. For example, I will give you some conclusions from the use of Alena tensor, which I calculated literally yesterday. And the preprint with the solution have been published an hour ago. Yesterday, I managed to calculate what the Dirac matrices used in quantum electrodynamics are. And it turns out that in this classical description, it is just something that is called polarization magnetization tensor. And moreover, it follows automatically from the equations that charged elementary particles must have spin. So it just comes out from the box. Moreover, the mechanism of mass formation also emerges automatically from Hamilton's description for point-like particles. Maybe more precisely, there is an energy gap in the equation, which the charged particle fills with the mass. And this is kind of mechanism of request for the mass. So this is why it comes out suddenly for particles, and so on. Because now you can count and discover as much as you want. So it's only the matter of time that you are able to spend by calculation or on calculations. And to sort out what I actually discovered, let's go through the first two publications. I will try to explain you what was in these articles. So on the slide number 6 are the most important conclusions from my first article on this topic, which was published a year ago. So it's quite long ago. In this article, I introduced a correction to the relativistic continuum mechanics, which causes the appearance of a natural relationship between objects describing density and the curvature of spacetime, which means in this flat spacetime picture, you have density, and then if you switch in equation the slider, you have curvature of spacetime. For example, charge density or mass density, any density tensor, flows smoothly into the curvature of spacetime. I also derived the relativistic Cauchy equation and showed that there is a completely mathematical transformation between curved spacetime and flat spacetime. I also showed that with such a description, the problem of dark matter and dark energy disappears. Probably disappears, to be very exact. Maybe saying more precisely, in Alena Tensor description, the cosmological constant must exist, and now if we use it, we know what it is. It's called some object that is called field invariant. It's hard to explain to people which don't use physics, but I hope that people with this knowledge understand that what is it. And it solves a large part of the problem of, for example, dark energy. Moreover, it also generates solutions free of non-physical effects, such as black hole singularity, because in this curved spacetime, we have a group of de Sitter solutions, which are free of non-physical effects, like singularities. So at that point, I would agree exactly with Professor Kerr. Instead of dark matter, there is an additional curvature term, which in the flat spatial description corresponds to some certain additional force. And I was really long thinking about what is this force. And this week, for example, when describing electromagnetism, I calculated that this force results from something that we already know, and it's called Abraham-Lorentz effect. This is some kind of effect that it's a kind of guard of energy conservation. I mean, when particle is moving faster and faster, it cannot just use energy from nowhere. It just uses energy from the field in the system. So at some point, the force has to decrease because we have less and less field in the system. So this is exactly this force, and this is suddenly it appears that this is part of this curvature term, and it becomes something. It may act or should act exactly the way that dark matter acts. What may be very interesting, especially for people who are making research in this area. So in the second article, you may see on the slide 7, I focused on the connection with the quantum description, and the main conclusions from this article are as follows. I have shown that use of Alena tensor gives a relativistic Lagrangian, both for continuous media and for the description of point-like particles. I also showed that it is possible to freely move mathematically between general relativity, continuum mechanics, quantum field theory, and classical theory. So I have shown that this bridge works, and we are able to switch from different descriptions, and the description are equivally valid. Okay, which means we are able to understand this theory as something. There is class of theories which says that this is a dualistic theory, because we are able to describe the same thing from different frameworks of different theories. So this is exactly how it works. Okay, but cool down your enthusiasm, at least a bit, because it's worth saying that you shouldn't expect any quick changes in science. Science doesn't like revolutions, doesn't like innovations. And you have a quote to prove it on the slide number 8. In fact, the more innovative something is, the harder it is to read. It's harder to understand. It's harder to use because you have changed your habits. And often it's rejected if it doesn't fit our established beliefs. So, for example, I have some correspondence with my colleagues from physics. And for example, one of the reviewers sent me following report that he checked all the calculations. He didn't find any mistake, but he's against publication because it cannot be true. Okay, and it's hard to change the perception sometimes. Of course, my article aroused interest, and I know that at least a few physicists will develop Alena Tensor. But overall, I expect rather a lot of criticism in the first years, because this is how science works. Okay, that's not a bad thing. I think it's not a bad thing. Slide number 9, you have something that I called adaptation of innovation in science. Slide number 9 shows that the adoption of innovations in science is progressing in a certain, let's say, quite schematic way. The first instinct is to criticize and try to undermine the results. And that's a good thing, by the way, because it eliminates all unverified and false works, which has been appearing a lot lately, by the way. Can you hear me? Pardon me?
Yes, we can hear you.
Okay. When I have no response, it's hard to be sure that everything works fine. Okay, but when this approaches to falsify the theory, when it fails, the initial interest arises and it leads to further research, which, of course, after publication, these published articles with subsequent research, result in another wave of criticism. And only after many years, the innovation is adopted. For example, it took quantum mechanics many years to achieve this, as did general relativity. So don't expect that anything will change in, I don't know, months, for example, or weeks. I expect it will take about maybe 20 years for physics to adopt this discovery. So if it will be confirmed, because there's always some possibility that that's not correct. And by the way, it's maybe even a good thing in present circumstances. There is, maybe you don't feel it, but there is a war going on Europe. This war is about 100 kilometers from my home. So it, for example, could turn out that I don't know, my discovery may lead to some possibility of developing some new weapon, for example, like it was with previous innovations. So I'm already a little worried because, in fact, the largest group of scientists who read my article are scientists from Russia. So who knows? Okay. But anyway, let's focus on what known possibilities open up with this use of Alena Tensor. So on slides 10, on slide 10, 11, and 12, you have a list of potential consequences, which of course not exhaustive. There's a lot more, but at first there is a good chance that this approach will explain the problem of the cosmological constant and dark energy, as I mentioned. Similarly, with the dark matter, which is just no longer needed. With the Alena Tensor, you have some additional force that should be responsible for dark matter. Thirdly, the mechanism of gravity formation was described. And what is really interesting in it, by the way, for this part of you that don't believe that you are able to strain curved spacetime, in this flat spatial description, when you make this curvature flat, I mean, when you strain the spacetime, the gravity appears to be something, some phenomena. The easiest words I can say is bending of the direction of the field energy transport by the energy density gradient, which means it's not interaction between bodies. And this is exactly what we should expect from gravity. I mean, if this is really kind of curvature, this is not interaction between bodies, then we should have something that should act like curving the light path. So this is exactly curving the light path, bending the direction of field energy transport. It's curving the light path, and exactly the in this continuous description, this is not exactly light path, because then we use description, continuous description. So this is something which is called pointing vector. So this is curving bending the direction of the pointing vector. Space research will be also significantly simplified, if I'm right, because everything can be calculated just in flat spacetime, you know, and smoothly transferred to curvilinear description. For example, we have a lot of troubles and use a lot of tools in numerical relativity to calculate some complex systems. And suddenly it appears that you are able to calculate this on flat spacetime, you get the result, and then you are able to switch to curved description. So it would be just fantastic. Alena Tensor also shows that something which is, I would say, not exactly physical, because it shows that all spacetime is actually some certain way of perceiving the field. This causes, for example, that inertial frames disappear. Because if we consider, if in these equations, if we consider a system in which there are no fields and no forces, then just equations simply turns to zero, and spacetime disappears. So it appears that that the spacetime around us and all of this you see is just a way of perceiving the field. So I understand that it's much deeper than just physics, because it will say what this space-time around us really is, okay? And you're able to calculate it. This is not just belief. You may see this on the equation that indeed, for those who knows physics, to be very exact, the metric tensor responsible for the space-time curvature is related to the field tensor. So if field tensor goes to zero, then automatically the whole equation disappears, and it's very, very, I would say, deep consequence. Assuming that I'm right, it will be finally possible to move smoothly between curvilinear description, classical description, quantum description, and so on, because it will be explained what the quantum description is and how it is transformed into a classical description. It also explains why quantum gravity was, by the way, so difficult to find. If you read the preprint I mentioned, this preprint published today, you can see that by describing the particle as a polarization magnetization tensor, we are, in some sense, we are absorbing gravity and this additional force that I mentioned about the dark matter into the spinor description. So if you calculate, for example, quantum electrodynamics calculations, and you take a look at this equations, you don't see any gravity there, and you don't see any additional force related to this the dark matter, because it was absorbed into description of the particle. I don't know if you are familiar with how we are doing dealing with this description of the particle. There's something which is called Dirac matrices. We use some spinors and so on. So we understand particle a bit differently than just, I don't know, ordinary matter or ordinary matter. Okay, so we have some constructs proposed by Dirac, and I show in this latest preprint that by this construct we indeed absorb gravity and additional force. So the only force that we see then is electromagnetic force, because the spinors and all of this Dirac proposed seems to be, at least in the description coming from Alena Tensor, seems to be something that is, to be very exact, it is polarization, magnetization, energy tensor. So it describes changes in polarization and magnetization. And what is very interesting, we have already found out that there are some objects which are called Jones matrices and John spinors and vectors. And there are some very strong relation to symmetry groups, exactly like with the quantum electrodynamics, for example, of quantum field theory. We also discovered this for polarization and magnetization. So it appears this is exactly this kind of mathematical apparatus that we should expect, and it really comes out from this equation. In general, everything in physics, I suppose, would become much simpler. Probably hundreds of new areas of research would open, because everything will be able to be transcribed into a description using Alena Tensor. And you can just make some calculation and come see what comes out from the calculations, just like I do it now. And who knows what else we can discover. Probably, the sky is the limit. I have no idea what I can find in these calculations for the next weeks. Many of you are probably wondering why Alena Tensor has such a name, because I had questions about it. So if you scroll to slide 13, everything will become clear. I was wondering how to name this tensor, and taking into account its properties, that is, it combines contradiction and incompatibilities that seems irreconcilable. Understanding it takes patience and a lot of mindfulness. Really, it's not easy to be learned. It can produce some deterministic results, while at the same time is behaving non-deterministically because of this polarization magnetization matrix. And it looks modest and beautiful at the same time. So, I came to the conclusion that this tensor is just like me, my fiancée. She's Alena. His name is Alena, and Alena is very calm, very quiet, and very good person. And for this reason, few people know how valuable a person she is. Our attention, is usually drawn to loud people, to loud and overconfident people. That's why I decided to name this tensor after her. Because, if I'm right, I hope I'm right, and Alena Tensor causes an explosion of new research in physics, the whole world will know her name and she will be remembered forever. So I wish her that it will happen. What's next for the Alena Tensor, you may ask? Of course, I continue myself to research this tensor, and some very interesting things comes out. But I decided not to publish everything myself, because I don't want to create my own information bubble. And if it's supposed to be unification theory, or maybe some founding for unification theory, then in my opinion, I should engage community. I even write about this in the articles, or both these articles. The more I research on my own, the harder it will be for other physicists to learn it, because it's not a simple theory. For example, let me give you an example. I have already calculated, I would say, most of electroweak interactions, and I wanted to publish them as an article, but I changed my mind. I understand that it's exactly it's building my own information bubble. So instead, I decided to systemize knowledge about Alena Tensor together with my a colleague from Jagiellonian University in Poland, in Krakow, and encourage scientific community to conduct thorough research and for criticism. I personally, I believe that only by working together, when and as a community, we are able to discover and change the world. So I decided that okay, it's maybe takes a year more, or maybe 2 years more, but it's worth it. Wait. Okay, and what more? What more? I suppose, there's definitely a lot to explore. For example, if you'd like to make a research in this area, it's probably one of the first areas is to describe subsequent fields and investigate the relationship with gravity. It's also a good idea to reproduce known results in a new mathematical framework, this based on Alena Tensor, which, for example, would be very advisable for phenomena such as Hawking radiation, or something that we call Uruch effect, because we don't have many tools in some areas in physics, which are when quantum mechanics is considered in strong gravitation. And Hawking radiation and Uruch effects are exactly this kind of effects, when suddenly you have to deal at the same time with very big, heavy objects and with quantum phenomena. So it would be great to calculate it in this new framework. You can study dark matter, especially since, according to Alena Tensor, it's not matter. I mean, the source of this force in the picture provided by Alena Tensor is not mass, it's not matter. So we call it dark matter, but it comes out that the source is different. And if you read this article, you probably see that indeed the source of this force have not much to do with matter. The same applies to research on the distant future and past of the universe, and dark energy, of course. What more, I also think that further development of relativistic continuum mechanics is also worth attention. Probably many other areas, many other directions of research. Because indeed we have just new tool, like you have some, I don't know, new tool in mathematics or in physics, when you have some new tool like tensor, okay? And when you calculate something on old-fashioned style without tensor, you have to do a lot of calculation to do the same using more advanced tools. So Alena Tensor, from my perspective, is just such kind of tool. This is just a bit more advanced tool, and it's much easier to use it when you have learned it, when you understand it. So I hope there will be people who will decide to spend their time to get known better this tensor. And I think that's it from my side. I hope I made you curious, at least, and that maybe you feel the need to ask the questions. If there are physicists with us, I encourage you to ask questions about the more technical aspects of this theory. I'm also open to criticism. In my perception, all progress so far has come from questioning previous knowledge. So if I can answer to your question without having to do any calculations, then I will try to answer right away. So, dear guests, dear listeners, stage is yours. I'm open for your questions.
Yeah, thank you so much, Peter. And yeah, just like what Peter said a while ago, we are now opening the stage for questions from the members of the audience, and you can raise your hand, and we will bring you up the stage. So this is a very interesting research, and actually, Peter, I would just like to say that to introduce your topic and other social media, I had to write some short description of the topic, and of course, in order for me to inform the audience, I tried to look at the Alena Tensor because I didn't know about it before. And when I tried to look at it, I realized that it's only very recent, that I thought that it was a previous theory that you just tried to anchor on and, reinforce it or use it as a tool to guide your research. But I found out that it's very recent. So um, I would just like to ask you at this point to clarify, and especially to those who just came in. So, are you the one who created this Alena tensor?
Yeah, this is me. Exactly. I have created this tensor myself. I feel responsible for all the effects, and I even gave the name for this tensor. However, to be very exact, the idea about transformation between curved spacetime and flat spacetime with forces is, it's known. Well, it's known. I mean, mathematics has a lot of explanations how to do it. So this is not that I invented some idea of doing it. I just described it. I mean, I just shown how to do it for the space time and how to fit this into the to the general relativity and relativistic continuum mechanics. So yes, Alena tensor was built by me based on existing mathematical bricks.
Yeah, thank you. So, I have more questions, but I will pass the mic in a while to those who came up on stage. And I would just like to introduce our guest speaker again for those who just came in the room. So, our guest speaker, Dr. Peter Ogonowski, is an experienced researcher, manager, and lecturer, a manager with over 20 years of experience, lecturer, author of a series of lectures and trainings, a researcher, author of publications in physics and management. In 2010, he was selected as one of the four experts consulting planned changes in the rules for co-financing innovative projects from the EU funds in Poland. In the years 2018 to 2022, he was a member of the expert group in auxiliary body at the Chancellery of the Prime Minister of Poland, and he conducts classes for first and one and two degree students and for MBA students at Kosminski University, University of Management and Banking, University of Logistics, University of Personnel Management, and National School of Public Administration. So yeah, please check out. There are two articles. There was one article who just was recently published. So it is here on the room chat. And yeah, for that, as of this moment, I would like to pass the mic to two of our speakers. And of course, Frank is one of our regular moderators here in Quantum Photonics. And maybe Bob will read later some questions or comments at the room chat. So, as I explained earlier, when we started out this room, probably some of your questions might be addressed. I'm not sure. He might be able to address it now, but some might be addressed the next time when he comes back here in quantum photonics, because we had talked about some problems, about some processing English sometimes or expressing what you wanted to say uh, yeah, verbally here in this audio app. However, it seems to be quite okay, Peter. And that I know that you're a great lecturer, well experienced and a professional one, and it seems as if you presented your work very well. So
Thank
at
you.
this point, yeah. So I'm quite surprised. It was very systematic. Well, many years of practice here, and plus the fact that you are an independent researcher, so that also gives it more zest. So I'd like to pass the mic to Frank. If Frank would like to speak now, I'd like to pass the mic to him, and later on to Eric. Frank, would you like to speak now?
Can you hear me?
Yeah.
Okay. So it says my connection is poor. Yeah. Yeah. Thanks, Peter, for give us this wonderful piece of your work, and it's I'm learning all the basic of the subject, but as a also as an engineer, very fond of physics, so I'm actually learning a lot. And but I guess I just ask some pedestrian, amateur from an amateur angle, that usually when we have a big discovery in science, usually the first thing the general public will be able to also ask is the what uh, experimental facts that your theory that most conveniently can be verified, that you can point to.
Okay. So let me answer this way. If I would invent some new phenomena, then we would need to confirm this with data. But indeed, actually, I just give a framework that explain existing theories. Like, for example, the something which is called Lagrangian density that I have calculated for quantum electrodynamics. This is exactly the Lagrangian density that we use. So it's hard to confirm it once again. I mean, it just we know already that it works. I just show why it works. So I just explain what are these Dirac matrices, and that this is related to polarization, magnetization tensor. And I also show how to transform it. I mean, transform it, for example, into the description which is for general relativity purpose. So when you go to general relativity, you get exactly general relativity equation, which is already known and was already confirmed with cosmological constant, with the Sitter solution. So we already know that for cosmology, for example, the Sitter is the main group of solutions that we use. And it's also hard to confirm because general relativity is already confirmed. I mean, we don't know better idea. But of course, there is a small trick in it, because I said that there is explanation for dark matter force. Of course, there's an explanation for dark matter force in this approach. I mean, there's some additional curvature term, and I'm currently in progress to calculate it to show if for at least some systems it works, and I hope it will be finished probably in weeks. So yes, it's possible to confirm it this way, showing exactly that it works. So this is one of direction to confirm it. It's also possible to look for some confirmation which is experimental, because this field tensor, this field invariant for electromagnetic fields, we are able to estimate, for example, for the early universe, from how to call it, just a second, from CMB. Yeah, okay. So from data about the early universe, we would be able to approximate this this field invariant and confirm, for example, then in this moment in the life of the universe it works. So this is also some, let's say, vector of confirmation. And I'm not at the moment. I'm not in it. It requires digging a lot of data, so I decided that I will do it next. Okay, and probably there are much wiser people than me in this area, so maybe somebody will be interested to confirm it based on this evidence. What more is, you, for example, get the relativistic force, which is electromagnetic force, which is known, so you don't need to confirm it, and you also get some effects related to the spin and effects related to the reducing energy. So yes, this is possible to make it even more clear and calculate this and confirm that it's exactly on the same level, for example, of magnitude that these corrections that we know. However, since it agrees with the quantum electrodynamics, then I honestly don't see the need for confirming it. But maybe this is also some kind of, I don't know, exercise that maybe it would be good to do. So it's not such easy to make confirmation for it, because it doesn't add much more to existing knowledge. I mean, of course, it's innovative and it changes our perception and it makes some and experimental knowledge, maybe not knowledge as a whole, but experimental knowledge, because you get solutions that we already know. On one side, you get general relativity. On the second side, you get electrodynamics. On the next side, you get quantum electrodynamics. So I just showed that it's possible to switch between all of these theories, and so somehow I probably will have to think it over, because it's not so obvious for everyone. Even my colleagues that read this article, at first they ask exactly the same question: how we can confirm it in data. So when we discuss and I show them exactly what happened here and why we have already confirmation in data for most of these elements, then the discussion goes, okay, so what we can do more. And I'm still thinking what we can do more to show that it works. At that moment, I will say on the theoretical level, we see that it works. On the experimental level, we would need to have to dig for some data to explain dark matter and dark energy. It's possible, it's worth to dig for it, and I'm in progress in preparing, let's say, some confirmation. But I also hope that others will engage, and maybe this confirmation will come from experimental confirmation, will come from side I don't expect, or maybe somebody will invent something that, for example, that will falsify it. It's also a good solution if you falsify it something with data. So who knows? We'll see. Okay.
Yeah, so my signal was just recovered, and I hear most of your answer, and thank you for that. And so the current one of the big problems that physicists are battling with is quantum gravity. So now your formula, I get a feeling that I got impression, maybe incorrect, that your formula somehow is a equivalent way of writing. Say you mentioned that all these different theory came out from your tensor, and what's your comment on, what's your thoughts on, say, any hope, because we know that QED is quantum, and then would that similar quantization will also go into gravity in your, would that be somehow easier or more natural in your formula?
Okay. Yeah. Good question. When I consider when you consider quantum electrodynamics, we use some description of the particle, which is based on Dirac matrices, Dirac spinors and Dirac, let's say, matrices. And when we use it, we will not see gravity. And this is what I show, for example, for the last preprint, because the Dirac matrices adopt already a gravitational part of the tensor, of the Alena tensor. So of course it's possible to separate gravity from these matrices. And your question bring me some idea at that moment, because maybe it would be possible to make these calculations. Maybe I would even add this to the next version of the preprint, because when you take this gravity out, then you get some object which is much harder to deal with it. So the easiest way is just to perceive the reality as Dirac proposed, because it's much more easy to calculate, even if maybe easier to calculate. Okay, it needs explanation. I don't know if you were trying to calculate, any of you was trying to calculate quantum electrodynamics. You have it's a really a lot of work with calculating. So there you have, for example, infinities in solutions. So maybe not infinities, but infinity infinity sums. So it's not easy anyway. But if you take this gravity out, it becomes even much harder to calculate. But indeed, there is a problem of time and of understanding time, what exactly this time is. And in this article, in the second article, I proposed some solution which would explain why it's possible to switch between these theories. There is some approach which is called Gerow decomposition. And using this Gerow decomposition, we are able to understand space-time as some slides of space in time. So when we use this approach, then it's possible to deal with gravity to go with quantum description to the also to prove space-time description. However, I didn't even start these calculations to be very honest. But it's for sure it's worth it. There is a lot of work, you know, to confirm it or falsify it. So I really hope that other physicists will try to do it. But there is a way to calculate it, and it's for sure it's worth to do it. But there are some limitations of this method. I mean, we are not able to deal with quantum description exactly the way we would like to deal because we are limited to some approach. So, but I show that it's possible to go to the curved spacetime with such description. What more? And there is a problem with time which is partially solved because of something that I said that is the most intriguing effect of using Alena Tensor, because suddenly space-time act a bit like it is a medium. You know, we are for a very long time we're thinking about what the space-time is, and now it comes out that this is only the way of looking on field. So we are able to when we consider space-time as just a way of perceiving the field, then some problems with the dealing with time, you know, are thrown away. Not all, but some problems disappear. And what to add more? It would be for sure. It would be great, and I'm really happy that you asked this question, because it would be great to find exact explanation of the phenomena of time. I mean, since we are able to calculate it, then we should also be able to explain what is it. And maybe it's worth it. Maybe I should take a look at this, because maybe it would help to understand how to deal with time and what it is. You know, from calculations, for example, it seems that most of solutions you are able to simplify to, let's say, you're able to simplify to some functions based on velocity, not even for velocity, but for velocity, because first element of this four vector is based on velocity, and to magnetic field. So it seems that it also should be some kind of function of it. Okay, I would leave this question open, because I really would like to make some check before I would be able to answer with being very sure about this answer. For sure, it requires just checking. But what is the added value of this tensor? You are able to check it. You're able to calculate it. You're able to find the solution because you have everything in full relativistic description based on tensors. So you're able to calculate it and take some data from it. It's not always easy, but it's possible. Okay.
Yeah, thank you, Peter. So, Frank, if there's time, if you have more questions later, we will revert to you. In the meantime, I'd like to welcome Eric on stage, and yeah, I'd like to pass the mic to him. And after that, maybe Bob can read some comments and questions on the room chat. So, yeah, Eric, mic to you now.
Thank you very much indeed. And thank you very much indeed for that presentation. That was absolutely amazing. Very, very interested. So interested, I tried to write questions but down, but unfortunately I had a question and comment about most of the things you said, so I got a bit stuck and I thought, I'll just listen. And two things I'd like to ask you now, and I mean, the first thing I'd actually like to say, is there any chance of actually meeting with you after this at some point, not necessarily directly after, but at some point in the future, just to chat with you about this in more detail, because I don't think I'm going to be able to extract all the information I want to ask about you for this, unfortunately, right now. If we would have some time later on, at some point in the week or next week or something, I would absolutely love to have a more sort of detailed conversation about it, if you would have time. But that's up to you, of course.
Of course, I'm open. I'm open for conversation. First of all, I'm available on by email. So you have my university email in these papers, probably also in this preprint. I also use Facebook Messenger. So if you prefer, we may try to chat on the subject on the Messenger. So of course, I'm open for discussion.
Thank you very much.
I'm quite a busy person. I must admit, but I have time for talking. Most of great ideas. My approach is as follows: most of great ideas that people have doesn't come from sitting and looking, I don't know, at the bridge. Okay, they come from talking. They come from exchanging ideas, from discussing, from not agreeing with each other, and so on. So I'm really open for it.
Fantastic. That'd be awesome. Well, the very least I'll do is we'll email you probably a bunch of questions, and then if you want to ask them by email or set up a meeting, then we can do that. That'd be awesome. But in the meantime, I do have a couple of questions, points if I could, that I did catch in general overall. So I understand that the last years of Einstein, a couple of decades of his life, he was trying to bring quantum and classical mechanics together, but he was using it from the perspective, doing it from the perspective of classical only, and ultimately failed. And I think you mentioned, and I think ultimately that that's you mentioned about explaining the unified theory, but from the quantum mechanics, because ultimately that's the fundamentals of the universe. And can I confirm that you believe that? Did you say, or you understand that what you've done, the Alena Tensor is essentially sort of quite a big step towards doing that and having that unified theory, the two, or indeed was a critical ingredient of a unified theory? But that's my first question.
If you could just once again just say this question directly, because you said a lot. Okay, so the question. Okay.
In summary, would you say that the Alena Tensor was a critical ingredient in creating the unified theory between quantum and classical mechanics?
Yeah, I confirm, and I even suppose why we didn't find it before, and I suppose why it was so hard to be found for the last 100 years. Of course, all of this needs confirmation. This is as we work in science, so please always have some distance for it. I don't claim that I have already confirmed all of these aspects. So it may always happen that somebody will falsify it, and then of course I agree for such situation. But at that moment, it looks that it really works. I mean, it gives a lot of really great stuff, scientifically great stuff, as a result of calculations. But so assuming that this is the right way, I understand why it wasn't discovered yet for the last 100 years. You know, I was the biggest problems I had was with understanding how to put electromagnetism into the general relativity, and there was some mental barriers I had to crush to make this working. First mental barrier was that Einstein tensor is not exclusively responsible for gravity, and there must be some other force. So Einstein, when he was calculating this, he probably assumed that he found the gravity and he should add something to the gravity. So it appears that he didn't have to do it. I mean, in this meaning, Einstein was right from the very beginning, because but he didn't realize that. But this equation that I get, this is exactly general relativity equation with cosmological constant and nothing more. This is it. But in Einstein tensor, there is a gravity and something which is very, very small in most situations, and it may be big or maybe go high or may go down, depending of the transfer of energy in the system. So it was very, very hard to develop, because this is not even the electromagnetic force or whatever. This is some very specific force which comes from the effect I mentioned. This is it's the effect of let me recall, Abraham-Lorentz effect. So it was very hard to invent, and I understand that it was very hard to find. The second barrier, mental barrier, I had to jump over was when I saw that this metric tensor responsible for curvature of spacetime. This is exactly the field tensor. Then at first moment I said, okay, it cannot be true, okay, because it would mean that just spacetime is field. So we deal with fields a bit different way. So we assume that there is some kind of spacetime, and there are fields in the spacetime. I mean, most of way of thinking in physics is that some field is something additional to the spacetime, and suddenly it would mean that all of fields we experience are just spacetime, okay, some perception of spacetime. So I stopped and I tried to figure out where is the mistake, but there was no mistake in the calculation. So I said, okay, it's hard to understand, I have to think it over. And I was thinking probably for 2 weeks for some other approach, okay? So at the end I decided, okay, so let's check what will happen when we accept this, which is really hard to be accepted. And and at the end I got that it all works fine with this assumption, which would really, I understand that it may be hard for most of my colleagues, because it's rather extraordinary. This is not typical approach to field. So it was the second barrier. And the next barrier was that when people are looking for explanation of gravity in the let's say the classical physics, they mainly use Newton equation, which transforms, let's say it, into gravity in the way that Einstein understood it. But if you jump over these two previous steps, you don't get exactly Newton equation on the flat spacetime. You get something which acts and is very, very close to Newton, but is a bit different, which means that when you try to join something in this curved spacetime and in flat spacetime, you based on some existing knowledge. But if this existing knowledge is not exactly the solution, then it's hard to join something which don't fit. So it's much easier to show that it fits when you know already the result. So it was much easier. It would be much easier to know how Alena Tensor works, calculate all the forces, and then make interpretation of these forces, because you may look at these forces in 4 different approaches. In classical approach, this is one of approaches that's come out. But then you may switch to continuous mechanics approach when you deal a bit different with these forces, because then you have some forces coming from, let's say, coming from the pressure, and this is a bit different perspective than classical. Then you may incorporate part of these forces, the part of this tensor, to be honest, into this description of the matter, and then you have Dirac matrices. Okay, so and moreover, you are able to go to the particle-based, the point-like particle-based description, and deal with it through the classical Hamiltonian, and then you might switch once again to Schrödinger approach, and it all works in Alena Tensor, but really it all works. You are able to do all of these things, but it's, you know, it was hard to invent it. I mean, how it may be so elastic? Okay, it appears that yes, it may be. So when people are trying to figure out how to join something with something, they have to make some assumptions, and suddenly, for maybe even I try to explain it even more simple way. For example, when we are looking quantum gravity for quantum gravity, and when we are trying to find out how it works, we, for example, mainly use description of gravity which is not continuous. I mean, is not in continuous media, but in the classical approach. The same situation with, for example, with the classical forces like electromagnetism. So we just calculate electromagnetic force. We just calculate gravitational force. Okay, like force. But when this connection really is, this connection is not on the level of forces, but on the level of force densities. And it doesn't work this way, that forces on this particle level are the same as in continuous media, because in continuous media you have some other forces. For example, you have some force, let me translate it just a second. Okay, you have body forces, and you have some, for example, something which is called tidal forces, tidal forces. You have some different explanation for forces. There are some forces that comes out from the box when you consider continuous media. So if you are concentrated on the point-like particles, you won't see forces that comes out from continuous media, okay, which are described, by the way, by Cauchy equation. So it's hard to join something with something which don't exist in your description. So this is why it was hard for so long time, because I also had to understand that I should be looking for transformation not between classical theory or quantum theory, but at first I need transformation between general relativity and continuous mechanics. Okay, because this is exactly the level when the theories are talking about the same thing. So indeed, this connection, when I see the solution, I mean, when I understand what I've done, then now it seems obvious, yeah? But this is not so obvious for everyone, believe me. When I discuss, for example, about continuous mechanics with some colleagues working on physics, then they ask me, okay, why are you doing this on the level of continuous mechanics? It will be much easier to do it on the level of point-like particles. So it appears that's not true. Okay, you need to jump over or crush many barriers, mental barriers, to make this working. So this is exactly why I suppose it was so hard for the last 100 years. If this is, of course, I have to once again I have to say it. If of course everything works fine, and if I'm right, because I'm open for falsifying the story. At that moment, it thinks that it looks that it works, yeah. But falsifying theory is nothing wrong. So please do it if you are able to do it. This is as well solution as confirming it. But up to this moment, it rather generates really good solutions, and it appears that it works. So we'll see.
Amazing. Thank you.
Thank you, Eric. And yeah, thank you, Peter. So I'd like to pass the mic to Bob to read some of the questions or comments here at the room chat. Bob, mic to you.
Okay, so V states that you are an amazing guest, and I think everyone will agree with that. And she asks what originally inspired your research.
Okay, a great question. You know, the original inspiration of my research come from my father, because I have a father who is working with electromagnetism, and we were discussing years ago. I would say I was maybe 13. He's an engineer and he works with electromagnetic stuff. And we were discussing about the word, what the word is, and so on and so on. And at one moment, I remember this to this day. He said, you know, it may appear that all of this around us is just a wavering electromagnetic field. And I was a bit, I don't know, curious what he's talking about. But for some reason, I just remembered that it's strange. Yeah, it just sounds strange that all of us, the solid world is just a field. And when I was at some moment, I was working over over some research in physics. Then I reminded this because there something comes out from one of the solutions that looks like, let's say it, wavering word. So I said, okay, maybe I should take care about this approach. Maybe I will find something interesting. And I started to make some research, and it wasn't easy. But as longer I was working, as more I was convinced that my father was right. So the original inspiration comes from, you know, my childhood, from me being 13, really. What resonated for some reason, I have no idea why, but resonated with me for the last 30 years, because I'm over 40 now. So that's how it worked.
All right, that was awesome. Now, I have a second question, and this is from Kyle, who asks about wave function realism, rather.
Realism, wave function realism. Okay. I suppose that you are asking me about Copenhagen interpretation of quantum mechanics, or is it, I don't know, for example, second interpretation that we do more solid or whatever. You know, let me think for a second how to answer it, because one of the things that is interesting is that you are able at the same time look at something in the deterministic way and indeterministic way. So maybe let me explain it without using physics. When you, for example, press the button to use the lift elevator, it doesn't mean that the elevator will come. Yeah, you only increased probability of this event. You may not even come. I mean, we act and interact with the world by increasing or decreasing probabilities of events. Okay. For example, when you say to your child, to your kid, go to study and I don't know, learn something and so on, then you will be a wise man, or you will have success in life. It doesn't mean that it will happen. You only increase probability. I mean, there's always probability that you don't learn anything, you don't go to study and so on, and you are a millionaire, for example, of course. But this is rather smaller probability, which means we are trying to interact with the world by increasing and decreasing probabilities of events. And on this level, this quantum function is working really fine, because all we are able to do on the very small level, when we have wavering world, I mean, nothing has changed. There's a lot of sudden, how to say it in English, disturbances in this media, let's say it, which is space-time. Then this still works exactly the way that we observe this on the quantum level. So when we deal with particular elevator, you don't know if this elevator will come or will not come, because there is only some probability of it. But when you are on the very high level, when you go higher and higher, and you take a look at, for example, the whole United States, then you may say, with almost central, being almost sure, that mainly when people press buttons to call elevator, the elevator come. Yeah. So on the very high level, we have something which is called Bernoulli law, and suddenly it works, and you don't see all of these perturbations. So that's how we think about very big world around us, which is described by this, let's say, classical or space-time curvature description. So when you deal with very, very big objects on a big scale, you may just think in the classical deterministic way. But when you go smaller, when you go lower and lower and lower, you are not able to predict everything, because even from this calculation, which means from Alena Tensor, comes out that you would need to calculate all of polarization and magnetization spinors and know them in every moment of time, but they are interacting with themselves in the way which is unpredictable, I mean, which is nonlinear. And even small disturbance for some reason may change everything. This is like in chaos theory. I don't know if you know chaos theory, but probably you've heard about the butterfly effect. Yeah, even butterfly may change the weather in Tokyo. So this is exactly how it works. Even small disturbance in one region may when give you result which is completely different than original that you have calculated. So on the very small level, when you have this perturbation very close to to some objects in calculations, I don't know how to say it in the way which is understandable. Okay, on such level that this is important, then that's true. You cannot make predictions which you are able to be sure about it. Moreover, in this approach coming from Alena Tensor also comes out that if all is described by electromagnetic field, and we assume that electromagnetic field is quantized because photons are, let's say, like quantized, then you also get quantum picture. I mean, quantum in this meaning that you have a discrete picture. So I was even thinking about it yesterday, because literally yesterday I finished my calculation and sent the preprint to the preprint server. But I was even thinking about this yesterday and today before this event, that it would be great to find out why this is all in quantized. I mean, maybe there is some explanation in the inside these calculations. Maybe I need to find it, because it seems to me that it's possible. I mean, it's possible in that way that for some reason some levels of energy are forbidden. at least on the very low level of energy. But it's open question. I need to make some calculation. I cannot answer at that moment. So going back to your question, in my opinion, quantum mechanics is right with this Copenhagen interpretation. Okay.
Yeah. So I think Bob went out for a while. So yeah, Kevin just came on stage, and here on the room chat there was a comment from Ash. Yeah, what did you find when straightening out negatively curved space-time? And anyway, he said, oh, he got that already. And he came in late, so he didn't catch it earlier. So yeah. Anyway, we have Kevin who came up on stage. So Kevin, welcome. Would you like to speak?
Oh yeah, hi. Yeah, this would be like the third time me asking from these rooms, but with the new discovery of a quote unquote new magnetism, ultramagnetism, as a fundamental force, do you think this could affect your calculations?
Because Alena tensor may be considered for any field. I mean, you may just put any field tensor and calculate what comes out. So we may look at the space-time on the very theoretical way, like what would it be if we, for example, have different kind of field as a base field for the world. And it also leaves some open question: what are the number of these fields that space-time is made of? I have made a calculations for electromagnetism. I have almost finished, but as I said, I quit it for a while. Calculation for electroweak field, and it appears that it works the same, and it's quite easy to be calculated, to be honest. But for example, I have some problems with strong forces. It appears that they work a bit different. So who knows what kind of force this is? Maybe we need to make some small correction, for example, to one of this field to get strong forces. This is one of the hypotheses I consider. So I wouldn't say that electromagnetism is just that word is just electromagnetism at all. I would say that word is a field. Exactly what kind of field? What is more than electromagnetism? It needs to be, in this approach, of course, in this framework of Alena tensor, needs to be checked. For sure, for electromagnetism it works. For sure, for electroweak, maybe not for sure because it was not published, but with high probability for electroweak it works the same. So we could the same moment say that depending on the calculations we do, if we only consider electromagnetism, then world just appeared to be electromagnetic. Okay, media, let's say, made of electromagnetism. If we consider electroweak interactions, then the space-time is just the way we perceive electroweak interaction. But what is this fundamental interaction? I don't know. Okay, this is still open question. It needs to be calculated, needs to be checked, and this is not so easy. Not so easy because we deal with 5 or 6 different approaches to understand field, which should be carefully, how to say it, reconciled. So it really needs some work of the community. I don't believe that I'm going to check all of this myself. I don't even imagine it. It's a work for the whole community, and I hope we will be able to find a solution. What is this most fundamental field, or maybe fields? Okay, so I suppose I hope that it answers the questions. But when you neglect other fields, other forces coming from other fields, then you may just simplify all of this, that this is electromagnetism. If you want to deal with different fields that we know that exist, like electroweak, for example, then you need to say, okay, electroweak. When you go to strong forces, then it works a bit harder, and I don't know the solution, so I'm not able to open what, in my opinion, is this word made of, because I'm at that moment I have no results of this calculation. So I'm trying not to saying something that wasn't checked, at least.
Yeah, yeah. Ultramagnetism. I don't. It's part of the sort of the two flips of the coin. Two sides of the same story. But yeah, it just came out. So yeah, thanks for the answer.
Okay, I would add something. I will add something to this answer. It seems that electromagnetism is not enough, because we have something which is called symmetry breaking. I hope you all have heard about it. So it rather seems that we need something, like, for example, Higgs field, that we need something to describe reality. But believe me, it's so big amount of work and amount of calculations that I'm just alone. I'm not I'm not able to do it. So I would like to know answer for a question. I hope that someday, maybe in near future, I will get the result, or somebody will find it.
Thank you so much, Peter. So at this point, I'd like to ask you, how much more time do you have for us? So we've been here for
Oh my
about 1 hour and 43 minutes. So I think there are comments on the room
God.
chat. Yeah,
Okay,
I'd like to.
I have a meeting in 50 minutes. Yeah. Okay, the time is. I really like this discussion. Really, I'm really glad that you have invited me, and thank you very much for asking me to be part of this event. But indeed, I have, let's say, 10 minutes to the meeting, so maybe we have 3 minutes more. Maybe one question.
Yeah, so Peter, anyway, this guesting of yours here maybe has awakened a lot of people who might be listening to our replay, and they might have more questions. So I will see. Maybe they can give me a feedback on my Twitter account. If they have more questions, so that we can schedule a Q&A based on your study. Because anyway, you're a very prolific researcher, and I know that you just had mentioned that in a couple of weeks you have an update again about the preprint that you made. So I think it's good to plan on that, and we are very engrossed and interested, on we are following, we're rooting for your work. So
Thank
yeah,
you.
talking about the last questions, in the interest of time, I'd just like to read the comment of Pedram Nimrisi, who might be asking the last question here. Listening to Peter to think out loud, it's so cool. Would tune in for more and would like to see a GitHub to direct people and how to help. I For collaboration, maybe. I think some tuned electromagnetic AI should have a good impact on physics, from what I understand. So that is the comment of
Mhm.
Pedram Nimrisi. Thank you, Pedram, for making this comment. I was also thinking a little bit along that line. So, yeah, Peter, any comment on this? Because at this point, I'd like to, of course, thank you for being our guest. Very interesting. And of course, I admire you because you are also an independent researcher, meaning to say the passion is really there to work on the topic. So, do you have a parting shot for us?
Can I
I would.
chime in, squeeze in one more question?
Frank, I'm sorry, but Peter said earlier that he only has 10 minutes
Yeah,
because
yeah.
he has to prepare to go to
I
another
understand
meeting.
you
Maybe
have a
offline.
meeting to talk, but it'll be
Maybe
very
offline. Maybe offline question. Let me add one final comment. Um, since I'm not using social media probably as most of you present here, then if you have any question, you may of course ask me directly, or you may just you must join to questions that Cecile will send to me. I'm of course open for collaboration if there are some physics listening to me here, or physics students. There is a lot of issue we didn't mention. For example, let me say one final idea that I have already described, which I didn't mention. For example, from Alena Tensor comes out that we are able to shaping the curvature of the space-time with the field. So this is exactly why what is looking for to create something which is called warp drive in NASA, yeah, like completely exotic approach to use general relativity. I of course I didn't check anything about it. I didn't check if it works or whatever, so I have no idea if it's going to work. But this is kind of solutions that we may have. Okay, this is completely exotic idea which suddenly may comes out that it works. For example, so who knows what will be discovered, and I'm very glad that you want to be tuned with this with the development of this idea. I'm open. I don't have my Facebook webpage that I use. I don't use it, at least regularly. I don't have my Instagram and so on. So it will be the easiest way for me if you ask Cecile, and if there will be a lot of interest, we can always talk once again.
Yeah, thanks, Peter. Just quick comment as a moderator. This on our platform, we have in the past have invited researchers in similar field, experts on gravity and also quantum field theory. I do somehow I think it will be much to the benefits of our audience and the platform that if in the circle we can get a few to invite some your friends, colleagues in definitely know the material better than our amateurs here. Or we can invite. I mean, Cecile might invite some past speakers to have a panel, somehow deeper discussion. Just quickly, for your so I quickly glanced your paper, the first preprint. Seems that what you're doing, at least as given this a few minutes of reading, that you're building the relying on somehow continuum, the fluid mechanics, which is is continuum mechanics rely on the fundamental assumption of having a continuum, and for that we know the Cauchy momentum equation is in fluid mechanics. That's non-relative. It's a low speed, right? Yeah. So your tensor that can think of the solution of it is if it also works for if you build a bigger tensor that contains everything. So I'm thinking of what type of fields that your comes out of your equation is a solution of your equation. I do see somehow you at the beginning of your paper you mentioned that there's a neglect in the previous. There's a rigid body rotation.
Frank,
Seems it used to be neglected.
Frank, I wanted to interrupt you. We're burning the speaker's time. He has 1 minute to go for his next meeting.
I must go for the next meeting. So I'm so very sorry, but really I have to disconnect. I try to answer this question in offline mode. Okay. Thank you very much once again for inviting me.
Thank you so much, Peter. Maybe we'll invite you again. So, let's go to Darcel to lead us to do the countdown to close the room.
Thank you, Cecile, and thank you, Doctor. We'll get you out of here right quick. We're going to start our countdown from lucky number 6. Is everybody ready?
Ready.
Go for it.
6. Air at 5.
5.
Kevin 4.
4.
The great scientist Frank 3.
3.
Bob Dosek.
2 for me, please.
And Cecile Dosek.
2 also.
Good doctor, you're number 1. Call out our last number, please. That's you, Petrov.
Yeah, Peter, please stay one. You're still there.
Okay, yes, I'm there. 0.
Thank you so much,
Thank
Peter.
you
We
so
hope
much,
to see you
Peter.
back
We hope
in
to.
quantum photonics very soon. And please,
Thank you.
everyone, please check out our upcoming room. We have an upcoming newsroom in the evening, so please check that out. And once again, very grateful and appreciative to Peter. You have a lot of fans in quantum photonics, so thank you so much, and see you
Thank
all
you.
back in the next rooms.